In this video, we want to review the Riemann sum and introduce trapezoid rule. Okay, so I'm going to do this pretty quick. We're going to estimate the area of the function x cubed minus 2x squared plus 6 using, first of all, left-hand sum. So I just wanted to remind you, using a left-hand sum, if I'm going to break this into 3 intervals. So going from 0 to 1. Okay, what that means is a left-hand sum means the left side sets the height. So we go up here, go straight over. Now plugging 0 in to the original function, f of 0 is 6, so the height is 6 and the width is 1. The next rectangle would go from 1 to 2, and 1 would set our height. That height is 1, and the base is still a width of 1. And finally, from 2 to 3, 2 would set our height. And again, if you plug in 2, you're going to get 6. So 6 times 1. You'd add those up. That would be the left-hand sum. Okay. So the right-hand sum, of course, would just be using the other side. So the right-hand sum, we're going from 0 to 1. 1 would set the height. We already have found that. That's 5. From 1 to 2, 2 would set the height. We already found that. 6 times 1. And at 3, the height was 15. And we'd add those up. That would be your right-hand sum. Okay. Finally, the midpoint, now going from 0 to 1, okay, it's 0 to 1, 0.5 sets our height. So we'd set the height with that and draw the line straight across like that. Here 1.5, here 2.5, like that. We would use our calculator to figure out, what is f of 0.5 to get the height. What is f of 1.5 and what is f of 2.5. So that, again, we've done that before. This is just a review of the left, right, and midpoint sum. Well, today we want to talk about trapezoid rule. Now, trapezoids, if you remember from geometry, is a four-sided shape with 2 parallel sides. And the area of a trapezoid is 1/2 base 1 plus base 2 multiplied by the height. So it's essentially the average of the bases divided by the height. So here's how this is going to work. And I think from a visual standpoint, you're going to see that this is better than rectangles. What we're going to do when we go from 0 to 1 is we're going to actually find both endpoints, which we'd already done, connect them with a line. And of course, a trapezoid, remember, is 2 parallel sides. Well, those are the vertical sides are parallel. So this is 6 and this is 5. We did that in the previous slide. The next one, of course, we're starting here, going to 2, so we connect with a line. Notice that the concavity can, again, tell us, much like left and right, the concavity can kind of tell us here if we're over or underestimating. This we found was 6 in the previous slide. And the last one, going from 2 to 3, connect like that. So again, it is an estimate. I mean, it's not perfect, but I think you can see that it is a better estimate than the rectangles are. So now using this formula, let's 1/2 base 1. Well, base 1, remember the bases are the parallel sides. So the bases are, we always think of bases as being the bottom. They're not. The bases are, in this case, the vertical parts. So base 1 is 6, base 2 is 5, and the height is how far apart the bases are. Okay, so it's this distance, which of course is just 1. So that's the first trapezoid. The next trapezoid, base 1 is 5, base 2 is 6, and the height is still 1. The last trapezoid, base 1 is 6, base 2 is 15, and the height is 1. And of course, like all the Riemann sums, we just add these together, and that will estimate the area. Again, using concavity, we can say whether it's an over or under estimate. I think you can see here, it's concave up, so the trapezoid overestimates. Here we're concave down, so the trapezoid, maybe it's a little bit above. It is more exact than rectangles in most cases. Let's do one more example. Here we're going to talk about using a table, because of course in the previous example, if you had the equation, you could actually find the exact area by using the fundamental theorem of calculus part 2 and finding the antiderivative and evaluating at the endpoints. But if all you had was a table of values, and I'm going to make a quick sketch, I'm not even going to do any labeling here. I'm just going to say, okay, 0, 1, 1, 5, 2, 11. I'm not even going to label the axes. 3, 19. I'm going to be done right there. A left-hand sum, of course, would look like that, right? We use the left side would set the height. So the left-hand sum, the first one stretches from 0 to 1, so the base is 1 and the height is 1. It's set by the left side. The next rectangle, again the width is 1, stretching from 1 to 2, the height is 5. Next one, base is still 1, stretches from 2 to 3, so the base is 11. Okay, and I'm just going to stop there. The right-hand sum. Well, the right-hand sum, remember, would have the right side set the endpoint, so it would look more like this. Okay. So, base is still 1, but the height of the first rectangle is 5. Base is still 1, but the height of the next rectangle is 11. And the height of the next rectangle is 19, and again, I'd let you finish. And finally, trapezoid rule. Well, trapezoid rule, remember, connects them like this. Okay. So, we have 1/2, base 1 is 1, base 2 is 5, and the distance between them is 1. Okay, that horizontal distance. Next trapezoid, 1/2, base 1 is 5, base 2 is 11, and the width or height is 1. Next trapezoid, 1/2, base 1 plus base 2 multiplied by the width or distance apart is 1, and I would let you finish that. So this is probably the bigger use of the Riemann sum, is what if you don't have the equation? Or what if the equation you have you can't integrate, you don't know how? You can still find the area estimating with these rules. The trapezoid rule, again, is just a better way because it's, in most cases, more accurate. It is a little more work, the formula is a little harder, but the accuracy is usually worth it.